Greetings to all. This is group number 9 and for the DAA activity we'll be presenting on the topic Dijkstra's algorithm. These are my group members Sadhika Jain, Saumya Jain, Riya Gupta and myself Priyanshi Jain. So starting with the P class complexity. The P in the P class stands for polynomial time. It is the collection of decision problems with a yes or no answer that can be solved by a deterministic features in polynomial time. Talking about the features, the solutions of P problems is easy to find. P is often a class of computational problems that are solvable and tractable. Tractable means that the problems can be solved in a theory as well as in practice, but the problems that can be solved in theory but not in practice are known as intractable. This class contains many natural problems like calculating the greatest common divisor, finding a maximum matching, and decision versions of linear programming. I would like Sadhika to take over.
My name is Sadhika Jain, roll number 1, Dijkstra algorithm. One algorithm for finding the shortest path from a starting node to a target node in a weighted graph algorithm. The algorithm creates a tree of shortest path from the starting vertex, the source, to all other points in the graph. How does it work? Mark the ending vertex with a distance of 0. Designate this vertex as current. Find all vertices leading to the current vertex. Calculate their distance to the end. Since we already know the distance the current vertex is from the end, this will just require adding the most recent edge. Do not record this distance if it is longer than a previous recorded distance. Mark the current vertex as visited. We will never look at this vertex again. Mark the vertex with the smallest distance as current and repeat from the step 2. Problem statement. Suppose you need to travel from Tacoma WA vertex T to Yakima WA vertex Y. Looking at the map, as you looking in the diagram, there is a T, N, B, Phi and E vertexes. It looks like deriving through urban A, then mountain Rainer MR might be shortest, but it's not totally clear since that road is properly slower than taking the major highway through North Bend. A graph with travel times in minutes is shown below in the graph, as you can see. An alternate route through Etona Valley E and Backwood P is also shown in the diagram. Solution. Step 1. Mark ending vertices with a distance of 0. As you can see, we can mark y as a 0. The distance will be recorded in brackets after the vertex name. Now take over to Riya.
Myself Riya Gupta, roll number 4. Step 2. For each vertex leading to y, we calculate the distance to end. For example, NB is a distance of 104 from end and MR is 96 from the end. Remember that distance in this case refer to the travel time in minutes. Step 3 and 4. We mark y as visited and mark the vertex with the smallest recorded distance as current. At this point, P will be designated current. Back to step 2. For each vertex leading to P and not leading to a vertex, we find the distance from the end. Since E is 96 minutes from P, we have already calculated P is 76 minutes from Y. We can compute that E is 172 minutes from Y. Step 3 and 4. We mark P as visited and designated the vertex with the smallest recorded distance as current, MR. Back to step 2. For each vertex leading to MR and not leading to visited vertex, we find the distance to the end. The only vertex to be considered is A. Since we have already visited Y and P, adding MR's distance 96 to the length from A to MR gives the distance 175 minutes from A to Y. Step 3 and 4. We marked MR as visited and designated the vertex with smallest recorded distance as current NB. Back to step 2. From each vertex leading to NB, we find distance to the end. We know the shortest distance from NB to Y is 104 and the distance from A is NB is 36. So the distance from A to Y through NB is 140. Since the distance is shorter than the previously calculated distance from Y to A through MR, we replace it. We mark NB as visited and designated A as current since it now has shortest distance. Step 2. T is the only non-visited vertex leading to A. So we calculate the distance from T to Y through A, 160 minutes. Now Saumya will continue.
I'm roll number 6, Saumya Jain. Now, continuing with what Riya said, we mark A as visited and designate E as current. In the next step, the only non-visited vertex leading to E is T. Calculating the distance from T to Y through E, we compute it 229 minutes. Since this is longer than the existing marked time, we do not replace it. In the last step, we mark E as visited. Since all the vertices have been visited, we are done. Drawing the observation to the problem, we can say that we know that the shortest path from Tacoma to Yakima will take 160 minutes. Tracking with sequence of edges yielded 160 minutes. We see the shortest path is T to A to NB to Y. Pondering upon the applications of the same, it is used in digital mapping services in Google Maps. Second, social networking applications. Third, telephone network. Fourth, IP routing to find open shortest path first. Fifth, flighting agenda. Sixth, designate file server. Concluding the presentation, we can quote that Dijkstra's algorithm is an optimal algorithm, meaning that it always produces the actual shortest path, not just a path that is pretty short provided one exists. This algorithm is also efficient, meaning that it can be implemented in a reasonable amount of time. Dijkstra's algorithm also takes around V2 calculations, where V is the number of vertices in a graph. A graph with 100 vertices would take around 10,000 calculations. While that would be a lot to do by hand, it is not a lot for computer to handle. It is because of this efficiency that your car's GPS unit can compute driving directions in only a few seconds. Thank you. I hope that we explained the topic nicely.